Hello and welcome back. It has been a while since I recorded one of these because we had a week where I just gave you guys some time to get some work done before midterms, and then we had midterm week, which was where you took your midterm, and there was still nothing new. Then we had fall break, so it's been nearly a month since we have covered anything new. But I am looking forward to just jumping right back in. So I hope you have your notebooks ready, and let's just go. We are entering a new unit regarding population ecology, and I will talk more about what that means in a moment. But basically, our big question is how do changes in population size relate to environmental conditions? Your objectives for this week are to one, explain the relationship between carrying capacity and the availability of natural resources, and two, to compare the rate of change for different species populations using graphical analysis. So we'll be working on just these two things all week long. And before we jump into what all of those words mean, I want to talk to you a bit about these golden toads in Costa Rica. In 1963, it was rumored that during the first rain each year, thousands of golden toads would emerge out of nowhere, seemingly, and then quickly disappear. People were always talking about them, and scientists were eventually like, okay, what's going on here? No scientist had ever found them until Dr. Savage did in 1964. And yes, Dr. Savage was his real name. I wish that was my name, but could you imagine? Oh, that would be so fun. So, yeah. Anyways, in 1987, another biologist saw them too, but she noticed that many of the tadpoles didn't survive that year. So she predicted that the toads may not be around for much longer at that point. And 2 years after that, there was only one golden toad seen, and now this species is fully extinct. So, what the heck? What happened? What do you think happened to the golden toads, and why and how do population sizes change so quickly? What caused this is our big question. Here's some vocabulary you will want to keep an eye out for just throughout this presentation lecture. Population, obviously, we'll talk about exponential growth, logistic growth, carrying capacity, and limiting factors. So, what the heck is population ecology? Basically, population ecology is just the study of how individuals within a population interact with each other. And it's also the study of why some species populations increase dramatically while others go extinct. And if you're still sitting there like, what the heck is she still talking about? A population is just a group of individual organisms of one species that happen to live together. For example, a colony of ants. If you look at an ant hill and you see a bunch of ants, that is a population. Or even the human population. There's almost 8 billion of us at this point. Or, I don't know, a population of squirrels that lives in your neighborhood. These are all populations. So there's going to be different factors that determine how a population is able to grow. First being, well, there's many of these environmental factors that can limit population size, increase it dramatically, or force an extinction. We have, first of all, birth rates and death rates. So that's literally just when species or organisms are born and then organisms die. If you compare those two numbers, you can see is the population growing or is it decreasing? When the birth rate is greater than the death rate, the population grows. Obviously, we have a ton of babies, but not a lot of people dying or organisms. I shouldn't just say people. Then our population is going to increase. If you have the reverse, where there's not that many babies being born, but a lot of organisms are dying, you'll see a population decrease. And then we also have something called survivorship. This is just that different species have different probabilities of survival during its lifetime. And this right here is a survivalship curve. So if we look at organisms like humans, we have very few babies that are born, and most of them are going to survive. Like our babies are doing all right. But the older that the human gets, the more likely they are to die. On the flip side, if we have trees, you'll notice that trees will produce tons of acorns, but not many of them are actually going to survive and make it to adulthood. So a lot of the babies die off quickly, and then as they start growing, you see less death, but there's also less of those organisms, right? We also see this in like fish, where fish have like tons and tons of eggs, but it's like that scene in Finding Nemo where they have all those eggs, but only Nemo makes it. It's like that. Then we have this bird. I don't know what bird this is supposed to be. Maybe This looks like a duck and this looks like a hawk, so that's a problem. But birds will often have just a very consistent survivorship curve where they have a bunch of eggs and then some of them die and some of them survive. And then, like the adolescents, some of them die, some survive. And then some of the adults die and survive. There's not really a huge curve there. So, yeah, that is survivorship. Let's see, there's more factors that determine population growth. We have immigration. So that's when individuals move into a given area. And then we have emigration, which is when individuals are leaving a given area. So I think of like geese, for example, or no, geese are boring. Monarch butterflies, they will immigrate and come to a certain location. I don't even know off the top of my head where they like to go. And then when they're done, they will leave. So that's obviously the population is changing in that area as they're relocating themselves. We can calculate the population growth, and we're going to assume we have 1,000 individuals. The way that we calculate our per capita population growth is we have our birth rate plus our immigration rate, because these two are going to increase our population. And we're going to subtract our death rate and our emigration rate, because these two are going to decrease our population. If this number is positive, that means population is increasing. And if this number is negative, that means population is decreasing. Is that simple? Just some simple math there. Yes, I will ask you to do that. So we talked about what can change a population's growth. Now we're going to talk about how does that look graphically. First, we're going to look at exponential growth. So imagine there's a population that grows each year by 10%. So let's say they start with 10 and then they're going to grow by 10% the next year. So then there's 11 and then they're going to grow by 10% again. We don't go back to the 10, we're going to go to the 11. So the population's bigger, you're taking 10% of that. Then the next year, the population is bigger, take 10% of that. It's kind of like how interest works, but it's just increasing more and more at an increasing rate. In this example, let's say we have year one, we have 1,000 in our population. By year two, we have 100. Wow, that's not numbers. 1,100. So it increased by 100. By year three, we have 1,210. So it increased by 210. So you can see this jump went from increasing by 100 by increasing by 110, and then it will increase again by, come on, math, 100 and was that 29 or 19? I don't know. But you see it's increasing at an increasing rate. When a population continues growing at the same percentage, this is called exponential growth. And this is an exponential growth curve where you see it starting and population is increasing slowly, and then it just starts increasing faster and faster and faster. This only happens in nature when the starting population is small and there are good environmental conditions to allow this growth to happen. Where else have you seen exponential growth? I mean, the first one that comes to mind is COVID, obviously. I mean, I almost said a bad word. COVID just blew up, and we saw an exponential curve there with infection rates. So it's not quite population growth, but it's a similar mathematical relationship. Okay, so then we have logistic growth, which is a little bit different. Actually, it's very different. Exponential growth doesn't usually happen for a long time because something in the environment is going to force that growth to stop. So let's say we had, I don't know, like bacteria, for example, it's just going to grow and grow exponentially. Eventually, something's going to happen where this cannot keep happening. This is not sustainable anymore. That's where logistic growth comes in. Something that could limit that growth could be food availability. So we've run out of food. Obviously, we can't survive at that rate anymore. Or water or sunlight availability. Those are just 3 examples. These characteristics of the environment that limit a population size are called limiting factors. It's exactly what it sounds like food availability. Food availability is limiting how much growth we can have. It's a limiting factor. When a population has stopped growing, it is said that it has reached its carrying capacity. So every environment, every ecosystem has a limit that it can sustain. That's the carrying capacity. It's the maximum population that an environment can sustainably support. I had the definition right there. Did not even have to say it off the top of my head. So logistic growth describes how a population's initial exponential growth slows and stops because of a limiting factor. And here's what that curve will look like. So you'll see here we have our exponential growth. If you could just like cover this part, this is the exponential growth part where they're thriving, they're doing awesome. And then it's like, oh crap, we've run out of food and we're starting to die off. And we're just going to stop here because we can maintain our population at this point, but no more. That's the carrying capacity. The environment said, no, we don't have enough. This does not stay the same forever. If something changes in the environment, then the carrying capacity could change. Like, let's say you're looking at some shrubs in a forest and they have a carrying capacity of, I don't know, 5. And then let's say next to it, a big tree falls down, and all of a sudden those shrubs are receiving more sunlight. So that limiting factor has changed. And then they suddenly can grow more. And then new carrying capacity is 7. It changes just like that. It can increase or it can decrease depending on what's happening in that environment. So based on what you have seen, why do you think the golden toads went extinct? I'm not going to tell you yet. We're going to do some more math and stuff. But just think to yourself, why do you think they went extinct? If you're in person, I will make this an exit ticket. I'm so excited that you guys are going to be back. This is so good. Our assignment for this week is this population simulator. We're going to compare these two beasts. I forget what they're called right now. We're going to look at their population growth, compare them, do some math. It's going to be hard at first, but it'll be good. It'll be good. So until then, good luck out there. Let me know if you have any questions. You know where to find me. Hi. I will see y'all next time.